everybody. Today here I am going to show you how to find the shear force and bending moment in a propped cantilever. This is a propped cantilever having a concentrated load P acting at a distance L by 2. So it is at mid-span. Now we will draw a free body diagram. So in free body diagram there will be two reactions, RA and RB, and most importantly there is a moment MA because this is fixed support. That's why this moment at this point. Now our target is to find the value or equation for MA, RA and RB. So what we'll do, we'll first apply the equation of equilibrium. Summation of vertical forces equal to 0. So here vertical forces RA, RB and P. So easily we can write RA plus RB equal to P, and we can get RA equal to P minus RB. Again, applying the equation of equilibrium, summation of moment equal to 0. So here I have taken summation of MA equal to 0. This is a concentrated moment. So surely in equation we have to write directly this moment MA, but in case of load, as I am taking moment about this point, so in case of load RB multiplied by L will be moment for this point, so I am writing RB multiplied by L. This is anti-clockwise, I am taking positive. For this P it will be negative and multiplied by this distance L by 2 at this point. So easily we can get the equation for MA equal to PL by 2 minus RBL. These two equations we will use to find the reactions and the moment, putting the value of RB. So how to get RB? In the next slide we will see. Using deflection curve, we will find the deflection at this point for this load, as well deflection at this point for this reaction. So let's move ahead. This is deflection curve, and this is the deflection value del B1 or delta B1. At this point, actually this fixed support prevents rotation. So theta A, it is equal to 0. As well deflection also 0 here. Now to find the deflection, we can use double integration methods or moment area methods. So here I am using moment area methods. So what is the procedure to do that? First we have to draw a bending moment diagram for this load. So P acting here, if I take moment about A, surely it will be P multiplied L by 2. So here ordinate or the perpendicular or vertical this distance for this triangle, it is PL by 2. So we know this bending moment diagram, it is a triangular shape. So surely we can find the area of the bending moment diagram easily half multiplied by height multiplied by base. So base is L by 2. This ordinate height, it is PL by 2. So surely we get the area of the bending moment diagram PL square by 8. Because we are using moment area method. So we have to find this first. Then we need to find distance between center of gravity of bending moment diagram and B. So center of gravity of bending moment diagram, it is this one. I put here red marks. It is actually this base L by 2, 1/3 of this distance. It is from here to here, and from here to here it is 2/3 of this distance. So from here to here, because it is bending moment diagram, this distance between center of gravity and B. So I need this distance from here to here. So what will be that distance? 2/3 of L by 2 means we are taking from here to here. Now from here to here, already we know it is L by 2. So I put here L by 2, but in different way. The reason is I put the formula in such a way, suppose if both these distance are not equal, then we have to use, say, L. If it is A, then we have to use this distance as a L minus A. So according to that, I wrote L minus L by 2. So L by 3 plus L by 2 equal to 5L by 6. So we got the distance from B to center of gravity of the bending moment diagram. Now easily we can find that del B1 equal to A multiplied by this distance divided by EI. So this is PL square by 8, 5L by 6 divided by EI. Easily we get 5 PL cubed by 48 EI. That is the value for this deflection. Here I am using only the support reaction. I am not using this concentrated load because for this reaction I want to find this deflection. This is the deflection curve and this is deflection. Same as before, here fixed support theta A equal to 0 as well as deflection also 0 at this point. So same method I used to use. For these reactions I have to make a bending moment diagram. Very easy. RB multiplied by L, it will be RBL will be the ordinate or the height of this triangle, and we know this base is L. So surely we can find area of the bending moment diagram half height into base RBL square by 2. Now we need to find the distance between center of gravity of bending moment diagram and B. So from here up to here, surely it is 2/3 of L. So I wrote here 2/3 of L, so 2L by 3. So easily we can write the equation for this deflection equal to AX EI, putting this value A and X bar EI, I got RBL cube by 3 EI. So this is the value for the deflection. Now let's move in the next slide to bring those two deflection value in one place. Look at this. For the load P which acts at the midspan, we calculated already del B1, and for these reactions we already calculated del B2. Now we have to think of equations of compatibility, because here at this point B, del B, of course it is 0. 0 means these two, this minus this, must be equal to 0. So already we got del B1 value, this and this in the previous slide. So we brought that two values and we brought equal to 0, and putting this in the right hand side and cancelling which are common, we can find RB equal to 5P by 16. So once we find RB, surely we know how to find RA, because we know vertical forces, summation of vertical force is equal to 0. So easily we can find RA equal to P minus of this. It will give us 11P by 16. So we got two reactions. Here our target is to find the moments. This is free body diagram, and this is the shear force diagram. This is bending moment diagram. Already we got RA and RB in the previous slide. So diagram will be like this. Here there is a jump due to this load. So we are now applying equation of equilibrium summation of MA equal to 0. So already we got this equation before. MA plus RBL minus PL by 2 equal to 0. From this free body diagram we can do that. So MA equal to this. Now only the thing we have to replace RB. Already we calculated before what is RB. RB means 5P by 16. So easily we can calculate MA equal to 3PL by 16. This is the value here. MA. How to get MB? Not MB, MC, because MB here it is 0. So MC here it is RB multiplied by L by 2. Very easy, you know RB here. To get the moment at this section, we have to just RB multiplied by this distance, L by 2. So we get the moment for MC. RB already we know, 5P by 16 multiplied by L by 2, 5PL by 32, and this value it is here. So we got shear force diagram and bending moment diagram. That's all for today.